All right, 3.1, solving linear systems by graphing. Your objective or goal for this section is to solve a system of linear equations in two variables using graphing. Essential question that you need to pay attention to while you're watching the video and doing your work. Homework assignment is 1 through 5 in the homework packet. Vocabulary. System of equations is in two variables, x and y, consists of two equations or more. A solution of a system of two equations in two variables is an ordered pair that makes both equations true. So to check to see if an ordered pair is a solution, we're going to substitute the ordered pair into both equations. If the ordered pair is a solution for both equations, then it is a solution for that system. So let's take a look at an example. So we have point 2, negative 2. Is this ordered pair a solution of this system? So we have to first check to see if it makes both of the equations true. Then if it does, then it's a solution for the system of equations. So we're substituted in 2 times 2 plus a negative 2 equals 2. So I substitute an x and y. So I have 4 minus 2 equals 2. 2 equals 2. When the left side and the right side equal the same exact number, that means that this equation and ordered pair, the ordered pair makes the equation true. Let's try x minus y equals 4. X minus a negative 2 equals 4. So 2 minus a minus 2 equals 4. 2 plus 2 equals 4. 4 equals 4. And so because 2, negative 2 is a solution for each of those equations, it's a solution of the system of equations. All right, let's take a look at the next example. We're going to plug in for the 1, negative 3 into the first equation. 4 times 1 plus a negative 3 equals 1. Four minus 3 is 1. 1 equals 1. So that ordered pair works for that equation. So we have 2 times 1 plus 4 times negative 3. Does that equal negative 10? We don't. 2 minus 12 equals negative 10. Negative 12 equals, negative 10 equals negative 10. So this ordered pair is a solution for that system of equations. As long as it works for both, then it works for the whole system. All right, so solving a system of equations by graphing. You're going to graph both equations on the same set of axes, or in the coordinate plane. You're going to graph them both in the coordinate plane and then find the point of intersection. The point of intersection is the solution for that system. So let's take a look at an example. They have 2x plus y equals 2 and x minus y equals 4. We know that we're going to graph both equations on the same coordinate plane, and then we're going to find the point of intersection of the two lines. And as you can see, the intersection is at 2, negative 2. Remember, these are two equations that we use in example 1, so that is a true statement that 2, negative 2 is the point of intersection and is the solution for this system of equations. All right, let's take a look at the next example. example 3. So what we have to do first is find points on each of the equations and graph the lines and then find the point of intersection. So let's look at the first, we'll call this 1, we'll call this 2. So in this case, number 1, I can, x minus y equals -3. I can use an xy chart to find points on this line. If I let x equals 0, y is +3. And if I let y equals 0, x is -3. So I have 2 points. So I'm going to go ahead and plot those. 0, -3, I mean 0, +3, and -3, 0. Let's draw the line. All right, let's do number 2. Now, in this case, x plus 4y equals 2. An xy chart again, x and y. If y is 0, x is 2. But if x is 0, y is 1/2. 2 divided by 4 is 1/2. All right, so 2, 0, we're going to graph this now. 2, 0, 2, 0, and then 0, 1/2 right here. So now we're going to draw the line again so we can find the point of intersection. Okay, so the point of intersection, because I'm not using a ruler, it's off a little bit. So it does intersect at, the intersection is -2, 1, right here. So that's our solution for this system of equations. All right, I'm going to leave example 4 for you to try. I'm going to go ahead and do example number 5. In this case, we have, again, I'll label 1 and 2. I'm going to go ahead and solve each one to put it in the slope-intercept form. Remember, that's getting y by itself, so I'm going to add 6x to both sides. 2y equals 6x minus 8. Divide by 2, divide by 2. Y is equal to 3x minus 4. All right, so we know that the slope is 3, and it intersects the y-axis, y-intercept at -4. So let's plot those. Let's plot the point -4. And I know I have a positive slope, so I'm going to go up 3, and then over 1. Over 1. So now I have these points. I'm going to go ahead and draw the line. Let me get rid of that one. All right, so there's that graph. So let's go ahead and take a look at the other one. So we're going to work on number 2 now. -3x, so I'm going to add 3x to both sides. I get y is equal to 3x plus 7. So again, the slope is 3, and the y-intercept is equal to 7. All right, let's look at +7. The y-intercept's +7, so it's right here in the middle. A little bit higher than that, I guess. Get rid of this. Okay, so let's do that one more time. At +7 is right in the middle. Okay, then we're going to go we can go up 3, 1, 2, 3, and over positive 1. That's the other point. And then we can draw the line. Okay, so as you can see, the lines aren't intersecting. So what that means is it either has the same, and it's parallel, so it means it has the same slope. I don't know what that E is, so don't worry about it. But see if I can get rid of it. All right, so we have the same slope, which means the lines are parallel. The same slope, but different y-intercepts. So that means they're parallel. So the final answer is no solution. There isn't an ordered pair that you can put into both equations that will make these system of equations true. All right, I'm going to leave example 6 for you to try. There's some special cases that you need to know about. If the graph of equation in a system are parallel and do not intersect, then they have no solution. Systems with no solution are inconsistent. So if you had two lines, they have the same slope, different y-intercepts. Okay? If the graphs of this equation in the system are the same line, coincident, then the system has infinitely many solutions. Systems with infinitely many solutions are called dependent. So basically what you have is a line, and then you have basically a line right on top of it. I'm just going to show you. There's two lines there, but they're right on top of each other. Okay, that means there's infinitely many solutions. Systems with solutions are consistent. So let's go back real quick. So when you have parallel lines, it means no solution and they're inconsistent. If you have same lines, they're infinitely many solutions and they're dependent. And if you have one solution, they're consistent. So on this page you can see consistent means different slopes, intersects once, dependent, same slope, and y-intercept, intersect everywhere, and no solutions, inconsistent, same slope but different y-intercept, and they never intersect. Tell if the system is inconsistent, the equations are dependent or consistent. Okay, as you can see, I worked out this problem already, and I changed them from standard form into slope-intercept form, and what happened was each one of the equations have the same exact slope and also have the exact same intercept, which makes it a infinitely many solutions because they're both the same lines. So you can do the rest of the examples on your own by the information I've given you. If you have any other questions, please contact your teacher for more help.